Thanks for coming to my talk. I've never really figured out the elevator pitch for this thing, and whenever I describe it, I'm met with either the blankest of blank stares or reckless enthusiasm. So welcome, reckless organ enthusiasts. It's a safe place here. The Hammond Organ, the pinnacle of human achievement. I know a lot of you have been advised by your legal departments to never look at any patents. I promise that anything in here is long expired. Hopefully you'll permit me a brief introduction since I'm new to this stage. My name's Peter Teichman. I fight software for a living. This is what my face looks like, and I'm P. Teichman most places that you'd care to check. As an early heads up, I won't be taking questions as part of this talk, but please find me here online. I really want to chat about all of this. Spent the first few years of my career working on Linux on the desktop, in the first few years of Linux on the desktop. Hopefully some of you will remember this one. Any Simian GNOME users here? Any who weren't employees of Simian? Yay. By my reckoning, the true year of Linux on the desktop was 2001. But shout out to the Simian and the Easel people here in the audience. I worked on this custom netbook class operating system, sort of a Chromebook before Chromebooks, until the first wave of tablets swept that market away. This company, little, plays a small part in the narrative later. Oop. And now I'm at Fastly, an edge cloud platform. We extend existing cloud infrastructure to provide advanced application delivery and cloud security. I mostly work on image optimization, log streaming, and metric streaming, as well as, of course, leading our Hammond Organ synthesis team. But since years before any of that, I'd been smitten with the sound of the Hammond organ. I first remember noticing Georgie Fame backing Van Morrison, but I'm sure that I'd heard one before. The Hammond has been successful in most genres of music, but this talk's emotional center is instrumental soul, the stack sound, Booker T and the MGs, Green Onions. Why are you here? You're all accomplished Hammond organists sick of carting your instruments around. Now, as a software developer, I get this too. We're constantly fighting against unwieldy constructs and things that don't fit where we need to put them. Today we're going to replace your Hammond with a device that you could deliver with a single postage stamp. But let's take a moment to appreciate how far we've already come. The first Hammond organ was introduced as a portable version of this thing, the Telharmonium, in 1906, one of the earliest audio synthesizers. Like the Hammonds, the Telharmonium is an additive synthesizer. It builds its sound by summing together many individual frequencies, each the output of a sine wave oscillator. Additive synthesizers have an inherent parallelism that can make them difficult to implement sequentially. An additive synthesizer is sort of the reverse of a frequency display like you might see on a stereo, or if you've done work in the frequency domain, it's an inverse Fourier transform. So let's hear what it sounds like to add together two sine waves together. Here we'll combine a single frequency and then another one that's an octave above to make the waveform that's below. I'm not going to be playing anything live here. I angered the demo gods earlier this year with an act of hubris, but all sounds from here on out were produced by this talk synthesizer. So let's see. Very quiet at this point, but that's that. Like your Hammonds, the Telharmonium was also unwieldy. This console, first of all, requires two people to operate. The palm fronds are probably decorative, maybe load-bearing. But this two-person console isn't everything. This is just the user interface. Here's what's going on behind the scenes. This instrument is massive. If the Hammond is inconvenient furniture, then the Telharmonium was inconvenient architecture. Its weight is estimated at 200 tons, so your Hammond is already 3 orders of magnitude ahead. You'll see that the bill of materials here includes bricks and mortar. Only 3 of these were ever built, but they were designed for mass listening. The output was the telephone system. So you could call your operator any time of day and ask to be connected to the Telharmonium, then music would be piped into your home. You could take one of their provided paper cones and wrap it around your telephone receiver to amplify the sound, and there you have it. A voice-activated music streaming service in 1906. So for the better part of a century now, your Hammond's been a more convenient alternative to that monstrosity, but still not convenient enough. A Hammond B-3 with pedal board and bench is about 420 pounds. Nice. And a Leslie 120... And a Leslie 122 is another 140 pounds. In fact, once this talk was accepted at the conference, Alex asked me if I could make use of a Hammond if he could get one on stage. Of course, I said yes. I would probably embarrass myself playing to this crowd of professionals, but I would certainly try. I've always wanted to perform Green Onions on stage. He was able to locate a few Hammonds, but was unable to find anyone who would transport one for an acceptable fee. Once again, too heavy for its own good, so we have to make this thing lighter. This talk is about Roto, a series of embedded Hammond organ simulators that I've written for fun. My main goal in giving this talk is removing this 8-year curse. I apologize if any of you end up with it instead. I was really getting into Hammond music of various sorts around the time I started down the path that became my career as a software developer. Now my withered programmer arms are unable to lift the speaker, much less the Hammond itself. This is a super heavy organ. Most of my musical efforts went to the electric guitar instead, which is a favorite instrument of weaklings around the world. Roto started a few years ago when my work at Little turned briefly to embedded software development. This is a remote control for a set-top box that never made it to market. It has a wireless link to the computer and presents a USB keyboard, trackpad, microphone, and an accelerometer that we exposed as a 3-axis joystick. I really enjoyed working on this thing. After years of writing Linux desktop software and HTTP services, this was a totally different headspace, and it was really amazing to work on something that had physical interaction with the world. At about the same time, the Arduino was becoming really hot as a platform. All of these things bounced around my head along with a lot of Hammond music, and one night as I watched Cosmos, it felt like Carl Sagan was speaking to me and me alone when he famously said, "If you wish to make green onions from scratch, you must first invent the universe." So I started to slowly piece together that universe. What I'll present today is by no means the only way to model a Hammond and Leslie, and this is very firmly a hobbyist project, but I think it'll give you some guidance on how to start thinking about modeling some fairly complex instruments. I bought an Arduino and a MIDI Vox shield, a headphone jack, and a MIDI-compliant hardware interface by Colin Cunningham. This combination allows you to convert MIDI messages, which is a standard protocol spoken by thousands of hardware devices, to audio output. I wrote a program that took MIDI messages for the main user controls of the Hammond, its keyboard and its drawbars. Drawbars are a set of sliding levers used to shape the sound of a Hammond. My program read MIDI control messages and output an organ-like waveform. The Arduino ended up being underpowered for the task, at least as I understood it at the time. I attempted a design that was too true to the original Hammond sound, modeling each of its 91 oscillators individually. And given the strict timing requirements of audio programming, I was unable to mix those tone wheels fast enough to satisfy the audio sample rate. Audio programming is a real-time environment. Human hearing is extremely sensitive to fluctuations in frequency. In order to produce something that sounds good, you must output your waveform according to a very accurate clock. Tick, tick. If you're unable to keep up with the clock, you end up duplicating or dropping samples, and it sounds terrible. My Arduino implementation could only advance and mix about a third of the Hammond's tone wheels in the time it was given, so that was a showstopper. I briefly entertained the idea of tone wheel coprocessors, which would be additional microcontrollers that each produce a portion of the output waveform, but I never really attempted that project. I put it down for a few days, which turned to weeks, months, and then years. About 5 years later, I woke up one morning with a eureka moment. Simulating the Hammond's 91 oscillators looks kind of like this. You decide the volume of each based on the keys that are pressed and the drawbars that are pulled out, and then you advance and mix the oscillators. Each key that you press can activate up to 9 new tone wheels. This is computationally intensive, particularly on a slow-clocked microcontroller, and it's one of the main reasons why additive synthesis has a reputation for difficulty. So the oscillator frequencies in the Hammond are constrained by the gear ratios and machining techniques of the time, and they're very close to exact harmonic multiples of each other, but essentially running independently of each other. If I relaxed the requirement to model the individual oscillators and instead modeled their ideal harmonic relationships, then I can treat the drawbar settings as parameters for a more complex oscillator, build a single waveform, and play that back once for each key that's pressed, only one oscillator per key. That allows a normal trade-off in the synthesizer world called polyphony. We can do less work if fewer keys are pressed. It's not unusual to see an instrument that only supports 4-note polyphony or 10 notes or even 1. Many of the analog synthesizers that we know and love, like this Mini Moog, were monophonic. The Hammond, however, is a fully polyphonic instrument. If you press down all 122 keys, you will get 122 sounds. It sounds terrible. It's like a real cacophony. I guess that's cacophonic? Anyway, I feel it's an important constraint for simulating the instrument, so the Arduino was out for the synthesizer that I wanted to build. But with that performance realization, I decided to revive my project, but by then there were better alternatives to the Arduino. This is Paul Stoffringen's Teensy board, where the Arduino is powered by an 8-bit microcontroller. The Teensy is 32-bit, it's a Cortex M4. It does more work per cycle, has a higher clock rate, and has a much more flexible USB interface, so it can implement many more types of devices. And Paul supports a really excellent audio API. Out of the box and over one USB cable, the Teensy can take USB MIDI messages in and then output them over a USB audio device. In fact, I have the complete hardware developed environment for the synthesizer here. Or you can buy his $20 audio board, which is shown underneath the Teensy here, and then you get a headphone output and an SD card for storing sound files. It's really nice to build a small sampler. So let's define the scope for today's project. First, I want to implement a Hammond B-3 organ and Leslie 122 speaker cabinet, which is the most common model of speaker paired with a Hammond. Where there were differences over time, I kind of arbitrarily picked 1956 as the vintage for these devices. I want my instrument to be fully polyphonic, so we're going to be implementing 91 oscillators at the original frequencies. The Leslie is a beast on its own. It's a vacuum tube amplifier and speaker cabinetry with rotating elements. So, as the patent says, a rotatable tremulant sound producer. We all know what that is. The bass speaker is fixed to the cabinet, but has this scoop mounted to it that rotates around, throwing the bass around in a circular pattern. The treble speaker feeds this horn, which is mounted on a turntable, so the higher frequencies are also cast around in a circular pattern. The bass scoop and the treble horn spin at different rates and in different directions from each other, and a control on the Hammond allows you to select either a faster or slower set of speeds. So a lot of motion going on already, not to mention what happens when you place it in a physical space and get bouncing off of walls. We're going to control the instrument over MIDI, which is the musical instrument digital interface. This is a serial protocol standardized in 1983 for instrument control. Here's a hardware MIDI interface. I'm going to retcon this phone port here as another attempt at telharmonium-style music streaming. I welcome feedback, but don't you dare, well, actually, my MIDI fax phone port. MIDI messages look like this. We'll be reacting to node on and node off events as key presses, as well as control change events for knobs and drawbars and such. If you hear MIDI and you think of awful sounding synths, you're half right. As a control protocol, MIDI is agnostic to the sounds produced, but a lot of us were first introduced to MIDI by low-powered software synths in the early days of sound cards, and yeah, they sounded pretty bad. There have been traditionally two ways to get MIDI into a device, either this 5-pin DIN connector or more recently USB. Since the Teensy already wants a USB cable for programming and power, I'm just going to stick to that for now. As of last month, there's a third method. They've approved a standard wiring for MIDI over a 3.5 millimeter jack. That means that the Teensy audio board could also itself be a hardware MIDI receiver if you implement RS-232 serial. Most ports can be a serial port if you try hard and believe in yourself. For hardware, I'm going to target the Teensy 3.6, which is a $30 variant of the Teensy board that runs at a very speedy 180 megahertz. The Teensy audio API supports CD quality audio, so stereo output at 44.1 kilohertz and 16-bit values. The synthesizer will be controlled over USB MIDI and output either back to the computer or through the audio board's headphone jack. Here's a slide for those whose heads have been rotating with all the imperial units. The Hammond is 3 orders of magnitude lighter than the telharmonium, but our Teensy is 5 orders of magnitude lighter still. My kitchen scale isn't super accurate at this weight, but by my reckoning, you can send 2 Teensy synthesizers with 150-cent stamp in the United States. No problem getting one of those on stage for Strange Loop. Here's a to-do list as an overview of what we'll be covering. We'll start with a single audible sine wave oscillator, which we can duplicate to produce the Hammond's 91 oscillator block. We'll simulate the vibrato and percussion effects on the organ and control its volume with a swell pedal. Our 2 main building blocks for the Leslie will be a tube amplifier distortion model and a tremolo effect, which will integrate into the Hammond vibrato code. We'll use that to simulate the Leslie's 2 rotating speakers and then virtually mic the whole thing for stereo recording. All right, let's see what the Hammond looks like. Here's my block diagram of the Hammond B-3. It has this bank of oscillators equivalent to the big generator-looking things in the telharmonium picture. On the Hammond, sound generation is performed by spinning tone wheels that are shaped to induce a sine wave tone in a pickup, the dart-shaped pickup that's beside them. There are 91 of these in the Hammond, each producing a tone at a fixed frequency. There are 2 keyboards on the Hammond called manuals in the organ tradition. Each has its own set of drawbars. You can be playing 2 different voicings at the same time, but they're both controlling tone wheels from the same oscillator block, so everything ends up getting mixed together. There are 2 sets of drawbars, one for each manual. They control how much of each of 9 harmonic frequencies are mixed in for each key that's pressed down. So each key will trigger up to 9 tone wheels, but 2 keys may activate the same tone wheel. Here's a closer look at one set of drawbars, showing the range of tones that can be activated by pushing down that single C key that's highlighted in the second octave. You'll get 5 different octaves of the same note, plus 4 other musically useful intervals. Here's an audio clip that plays the tones from each drawbar in order. You can see we already have like that. There's something very Hammondy about that sound with just these 9 oscillators playing together. So then there are a few audio effects. The oscillator output feeds into a vibrato and chorus circuit, which is the main onboard effect for the Hammonds. Here's what it sounds like to sweep through the vibrato and the chorus settings on a B3. A second effect called Percussion introduces a sharp transient sound whenever you start playing from silence. So I'm switching here to playing legato where the percussion's not triggering anymore because it only happens when you start from silence and then back to percussion. So the output of the whole thing goes through a volume or swell circuit that's controlled by a rocking foot pedal, and that just sounds like a volume change. Here's the swell pedal from a modern Hammond, along with a set of foot pedals for bass notes. These control tone wheels 1 through 12, which are shaped to produce a more complex tone. We're going to ignore them for the purposes of today's talk, but they feed into the same tone wheels, and the tools that you're about to get will allow you to implement those too. So the first thing we need to do is to get the teensy to make a Hammond noise, and to do that, we're going to model its set of oscillators. The Hammond's called a tone wheel organ. What does that mean? It produces its sounds by spinning these specially shaped discs next to the dart-shaped pickups that are beside them. Here's a top-down view. We're now looking at the edges of all the tone wheels. There are 91 of these in the Hammond's oscillator block, each shaped and geared to produce a sine wave tone at a single fixed frequency. We need to simulate the oscillator block, and to do that, we need to first build a single oscillator. So how do we trick a computer into making noise? We create an oscillating signal in the audible frequency range. So we have to calculate the output voltage at each point in time. 44.1 kilohertz means that we have about 21 microseconds to compute each sample, which is very constraining if you're used to thinking in milliseconds. You'll also need a very accurate clock to guide when you output that voltage. In fact, Lawrence Hammond's prior experience was clockmaking. Before the organ, the Hammond company produced synchronous clocks, which are clocks that are timed by the frequency of the AC power signal. This is a reasonably accurate way to keep time. Probably your stove or your microwave oven uses a synchronous clock, but occasionally that system breaks down. Maybe some of you were affected earlier this year when an electrical power dispute between Kosovo and Serbia cascaded to slow clocks across Europe by about 6 minutes. You'll see similar problems running a 60 hertz Hammond in a 50 hertz country, or worse, running on generator power at a music festival. For the first, the organ's going to run flat. On a generator, the frequency may be all over the place. The Teensy Audio API takes care of this clocking for us. You feed it buffers of 128 samples, and it will output each sample in time. If you're working with a different system, then you may need to configure hardware timers to give you an interrupt whenever you need to output the samples. All right, we have an accurate clock. How about calculating the samples themselves? We're going to use a technique that's called direct digital synthesis. This is a really powerful technique for producing any audio waveform, and it hinges on one really simple realization. You can treat an unsigned integer as an oscillator if you repeatedly add a constant to it. eventually the oscillator is going to overflow, it's going to wrap back around to 0, and you get this sawtooth pattern as a result. We're going to take that sawtooth and use it as an index into a lookup table for a sine wave. So we sweep through the sine output repeatedly. The Teensy has 16-bit signed audio output, so we'll make these in 16s, and we're going to make it 256 elements long. We'll maintain a 32-bit counter that we update as samples tick by. That becomes our sawtooth. We'll use its top 8 bits as our index into the sine table, so we don't have to perform bounds checking whenever we're indexing into that table. The overflow behavior on this counter means that we can keep adding to it, and it'll eventually wrap back around to 0. So let's add a constant increment at each sample. The increment decides how fast the counter overflows, and therefore how fast we sweep through that sine table. If we set the increment to 2 to the 24th, then at each tick, we're going to output the next sample from the lookup table, just one after another. We'll loop every 256 ticks, ticking along at 44.1 kilohertz. We now have a sine oscillator at 172 hertz, which is just above an F. And we'll see how to adjust that frequency in a moment. Here's a struct definition, kind of pseudocode for the oscillator, and a function that returns the next sample value. We increment the counter, we shift it to get the index, and then we look up the sine value at that index. We'll call the index into our table the phase accumulator because it accumulates changes to the phase or the shift of the sine wave, which makes the increment our phase increment. We can play anything that we want as long as it's one note. A truly one-note song is very boring indeed, so we're going to want to change the frequency of our oscillator. If we decrease the phase increment from there, then those top bits in the counter are going to overflow less frequently, and we'll get a lower frequency sine wave. If we increase the phase increment, then they'll overflow faster, and we'll get a higher frequency sine wave. Calculating that phase increment for a fixed frequency is maybe not obvious, but it is really easy. We divide up our 32 bits worth of counter by 44.1 kilohertz, and then multiply that by the frequency that we want. We can build a table of phase accumulators for the 91 frequencies in the tone wheel generator and maintain a set of 91 phase accumulators that track the rotational state of all the tone wheels. A nice side effect of this approach is that the remaining bits in the phase accumulator are an indication of how far you are between entries in the lookup table. So you can use those to interpolate between the indexed value and the next for higher precision and much better audio fidelity. So let's set the volume of this oscillator. We'll add a 16-bit volume field to each of the tone wheels because we know that we're going to need to mix them together based on different volumes, and then each sine wave oscillator looks like this. If you replace the sine table, this can be used to play back any waveform at any frequency and volume with excellent audio fidelities. This is a really great building block. On the previous slide, I shifted the result right by 16 bits when calculating the output sample. One of the things that I've gotten out of doing audio work is the ability to think in the number of bits that each value contributes to some result. Multiplying n bits by m bits gives you an n plus m bit value. You can then shift that either way in order to produce something in a different output range. Adding an n bit and an m bit value together requires one more bit than whichever is larger. And then again, you can shift that to wherever you want. This is hugely useful when you're starting to reason about whether adding together two things is going to overflow the 16-bit range of the output. So tying it all together, all we need to do to produce the whole sine oscillator block is to run 91 of these in parallel. So let's see what they all sound like together. So apologies to anyone who was dozing off. This sounds awful. So we're going to need to play only some of the tone wheels at once. Wiring up the manuals and the drawbars is a matter of handling the MIDI callbacks, and it's left as an exercise for you. We're going to move on. Back to the physical Hammond, the next focus is the vibrato and chorus circuit. Vibrato is an effect that causes a signal to waver in frequency, causing a chorus an effect that makes the sound fuller. The Hammond has 6 different vibrato and chorus settings. We'll sweep through them all again here and hear how they sound. So physically, this is implemented as a variable length delay line. I'm afraid that's not going to be easy to read. You can think of this delay line like a slow wire with a fixed writer on one end and a reader that moves back and forth along it. You could do the same thing with an exposed cassette tape and a moving read head. And maybe some of you recognize the setup from a physics class. It's a classic example of a fixed audio source and a moving listener, so it induces a Doppler shift in frequency. When the read head is moving toward the writer, the waveform becomes squashed. This shifts the audio frequency slightly higher, same as a listener moving toward a fixed sound source. When the read head is moving away from the writer, the waveform is stretched and the audio frequency is shifted lower. When this movement repeats back and forth, you get that wavering of the input signal. On the Hammond, this is created with rotational motion in the scanner block. Hopefully you can see a little rotational arrow there. The Hammond has 3 vibrato settings which adjust how far along the delay line the reader moves and therefore the depth of the vibrato effect. Then the same 3 depths are also available as chorus settings which mix the dry signal back into the vibrato. And the result is 2 voices, one wavering and one fixed, which gives you a much fuller sound. We're going to use a similar model to the physical one, a delay line with a fixed writer and a moving reader. The reader is going to scan back and forth along the delay line over time. Delay line is really easy in software. We'll use a ring buffer. The scanner in the Hammond produces a roughly triangular scan pattern, so this is what the read offset from the right head looks like over time. The read offset is just another oscillator, just like the sine wave. So all we need is a triangle lookup table, a phase accumulator, and an offset. A depth parameter, used exactly like volume before, adjusts the limits of the read head's oscillations and therefore the strength of the vibrato effect. Our next effect is called percussion. On the Hammond, this gives you a little chirp at the beginning of each tone. It disables one of the drawbars while notes are being held and instead applies its sound briefly as the keys are first pressed down. If any note is being held, percussion doesn't sound, and you have to release all the keys to get it back. A bouncy playing style allows you to sound percussive notes or tie existing notes together as desired. Percussion plays briefly, it's about half a second, but every key that you press down during that time can contribute a harmonic to the percussion sound, so several tone wheels may take part. At this point, we could implement this by adding a time component to the oscillator block and decaying the volumes of the tone wheels over that time period, but that really complicates the tone wheel control logic, which so far is only driven by those key down and key up events. So I chose to implement percussion by adding a second whole set of tone wheels with a volume envelope positioned after it. These are updated in the same key down and up path, and so they produce a continuous tone while keys are down, but they feed into this volume envelope. That plays the percussion oscillator at full volume when the key first goes down, but it rapidly decays back to silent. And here's the block diagram. Volume envelope is a typical synthesizer block and is provided by the Teensy Audio API, so I've just used theirs. Here again is what the percussion sounds like. I'm going to switch back and forth between a legato style that doesn't trigger percussion and one that releases all keys so that it does play. Here's percussion sounding. And here you don't hear it all. And then back. It's kind of subtle, but it's a really important part of the voicing of a lot of Hammond music. Percussion has a few controls that switch which harmonic is played, the length of the decay, and its volume, and these are all really straightforward to implement with this design. Last and maybe least, the Hammond pedal bar has a volume pedal called swell in the organ tradition. I've connected the MIDI signal for this to the output volume of the organ. So component-wise, we've built a bulk sine oscillator and an emulation of the Hammond vibrato circuit. We've added the Hammond's percussion effect and its swell pedal. Tying these together with the Teensy Audio and MIDI libraries gives a full simulation of the B3. For the purposes of time, I've glossed over a few things, but key click, loudness robbing, and harmonic leakage, if you're aware of any of those things, are all physical effects that are really easy to implement with this single volume per tone wheel design. This is the B3 just as Lawrence Hammond intended, but it's not quite what players wanted. Brief digression on the way to the Leslie. The Hammond B3 was introduced in 1954, but strip away the percussion and make some tweaks to the tone wheel generator, and it's pretty similar to the original Hammond A from 1935. That's the organ that was a quick success in churches and theaters where it replaced pipe and reed organs, a giant sound for giant spaces. This is where it got its gospel start. Reverend Clarence Cobbs of the First Church of Deliverance in Chicago, one of the first African-American pastors with his own radio show, replaced his church piano with a Hammond. And that's the seed that spread the Hammond to jazz, soul, rock, and most every genre of music, but first it needs a little something extra. So Donald Leslie was an engineer who felt the Hammond lacked something in smaller spaces. The Hammond's accurate oscillators sounded dull, shrill, and still to his ear. He designed a speaker cabinet with rotating elements to give motion to the sound of the organ and presented it to Lawrence Hammond, who hated it. Hammond sent him packing. He had no interest in changing the clockwork perfection of his organ tone. As an aside, it's hard to say whether Hammond intended for his organ to sound like anything in particular. Many accounts are that he was tone deaf and completely uninterested in improving the sound of his instrument. This is one of the reasons why the Hammond from 1935 does not sound any different from the last tone wheel Hammond produced. Leslie left Hammond's office and brought his speaker to market. Over the next few decades, Hammond fought hard against it. He redesigned the speaker connection in an attempt to obsolete existing Leslies. He forbade his distributors from selling it, techniques which we're still familiar with today. Let's hear what Leslie thought of selling into this hostile environment. I was amazed at all the publicity Hammond created for me by their continuous bad-mouthing of my products. This word-of-mouth advertising was so good that from the start until the company was sold to CBS in 1965, no advertising was ever needed. And my problem has always been keeping up production to match sales. This is 24 years without advertising, followed by a successful exit for Leslie's tech startup. It took a few years after Hammond's death before his company recognized the Leslie speaker for its contributions to the organ's popularity, and eventually it bought Leslie Production. By the way, I like to think that Don Leslie is the Strange Loop attendee in this story. He's building on a very solid engineering foundation, but taking things in a creative direction that nobody really expected. So let's look at the Leslie. Here's a rough diagram. We need to simulate the effect of the two rotating elements plus the growl of the tube amplifier when the speaker is overdriven. Here's a clip of the Leslie switching from slow to fast. The change is abrupt here. I haven't implemented the momentum of the moving elements, so it just goes directly there. So let's first take a closer look at the Leslie's bass rotor. The bass speaker has a baffle mounted around it, sort of a drum with a scoop to guide the sound. The baffle spins around the speaker and casts the sound around in a circle. The main effect of this baffle is a modulation of volume, since the sound is louder when it's directed toward you and is quieter when it's directed away. It's spinning in a circle, so it's roughly a sinusoidal rise and fall of volume. Modulation of volume like this is commonly called a tremolo effect, and we're going to need to build one of those. Next is the treble horn. This horn is effectively mounted on a turntable, so the speaker itself spins in a circle. You see two horns here, but only one produces sound. The other one is there for mechanical balance. This has the same tremolo effect as the bass speaker, since the horn's pointed toward and then away from you. But because the horn has length, the sound source also moves toward and away from you at the same rate. This is a radius of about 8 inches, so you've got 16 inches of delay at whatever the current speed of sound is between its closest and its farthest points. In the vibrato effect, we had a fixed sound source with a moving listener. Here we have a moving sound source with a fixed listener. Relatively speaking, these have the same effect. So if we adapt the vibrato simulation from the Hammond to modulate volume also, we can use the same bit of code for the vibrato in the Hammond, the rotating bass baffle, and the rotating treble horn. I've ended up calling this effect AM/FM because it performs both amplitude and frequency modulation. So here's the block diagram for our Leslie simulation with the two AM/FM effects highlighted. We'll need to split the signal from the Hammond into the bass and the treble signals, and for this we can use a filter from the Teensy library. I've set the filter frequency here to 800 hertz, which comes straight from the Leslie documentation, and sent the low and the high pass outputs to the two speakers. The Leslie also distorts when overdriven with a characteristic growl. So in front of this, we're going to need an amplifier simulation, and here's what the growl sounds like. The effect of this sort of distortion is a flattening of the audio peaks. When the signal is low, we want to treat the signal normally, but when it's high, we want to squash the peaks. This is called a soft clipping effect. We have plenty of RAM, and the total range of output values is only 16 bits, so we'll use another lookup table here. We could easily shrink the table if we need to by interpolating between values if necessary. Because the incoming samples are signed, we'll use them to index relative to the middle of the lookup table. You can see that 0 is marked there in the center. This has a roughly linear response in the middle of the table at low volumes, but as you adjust the swell pedal of the organ louder, then you drive the Leslie harder and you push your samples more into the flattened curves on the sides. That produces more saturated overdrive. So far the entire signal chain has been mono, but if you remember, the Teensy has stereo output. At this point, we have two choices. We can place this speaker, simulated, in a room and simulate the reverberations as it spins around, or we can simulate the speaker being mic'd for recording. The room simulation will replicate more of a live feel. The microphone is something that you might hear on an album. I did the latter because it was a lot easier. So here's a common microphone placement for recording a Leslie. You've got left and right microphones, each 90 degrees apart from each other and pointing toward the speaker. We could add stereo output to the AM/FM effect and track the rotation, the position that's relative to each of these two microphones, but that complicates one of our fundamental building blocks. There's not really any difference between the output of a single speaker with two microphones and two speakers, one shifted 90 degrees, each with their own microphone. So we'll create a whole new set of speakers, start them off with a phase that leads the first by a quarter circle, and call that the other channel. This leaves us with a nice stereo effect that sweeps between the right and the left channels as the speakers rotate. So for our model of the Leslie, we built a distortion filter and expanded the Hammond's vibrato simulation to handle volume modulation as well as frequency. We combined two instances of that new effect to simulate the Leslie's two rotating speakers and then duplicated that whole thing again to give us stereo output. So let's wrap the whole thing up. I hope you've gotten a sense of how to model the physical processes in the Hammond organ, the Leslie speaker, with a decent direction to head in for making your own noises. My code is up on GitHub in this Roto repo. If you're looking for a turnkey synth, prepare to be a little bit disappointed. It has the right shape of things, and it's a good place to see how to wire up the Teensy API into custom audio devices, but there are some known audio glitches at this point, and control is not fully wired up. So I expect my journey to continue there. And finally, I have the Hammond Leslie stickers. We passed some of them around earlier. If you didn't get one, then I've got way too many. Make sure that you place the Leslie speaker to the right of the Hammonds, because the AC motor on the left side of the organ tends to induce unwanted noise in the speaker. That should be obvious from the perspective on the two stickers. Now, I've always dreamed of playing a Hammond on stage. To bring things full circle, here are a few bars of Green Onions played through Roto, and thank you very much for your attention. It's the only song that I can play. I think that's it. Thank you.